gentlemen. Hi, ladies and gentlemen. This is Mr. Green. I am giving you this recording of our Class Connect this week because I am having to give STAR tests this week. I'm sure you're having to take a couple of STAR tests this week. It's the English STAR test, so English 1 and English 2 will be taking their test. But I didn't want you to miss out on this Class Connect because we got some important things happening this week. Okay? So, where should you be? Well, I'm going to do a review of Unit 3 here in just a minute, but I do want to look at area and volume ratios. And then after I get through with the review, I'll talk a little bit about arcs, and we'll get into that just a little bit. First of all, let's look at area and volume ratios. When we're talking about ratios, a ratio is nothing more than two numbers written down as a fraction. Okay, so it says find the volume of prism B if the volume of prism A is 1,120 cubic units. Well, we know the volume over here is 1,120 units. I can see that the side lengths have a ratio of 14 to 7. One of the things you can do is this side ratio will be the same for these similar objects. So all the sides are going to be in that ratio to each other. So we're trying to find volume. What are we going to do? We're going to multiply this times itself 3 times, or 14 over 7 cubed. Well, 14 over 7 can be reduced. I don't like dealing with that huge numbers. 2 over 1 cubed, which is going to be 8 over 1. Now, if I write that 8 over 1 as a proportion to the volumes, and remember, this is the bigger one, so it's 1,120 up here divided by x. We'll be able to figure out that 8x equals 1,120, or that x is equal to 1,120 divided by 8. And if we do that on a calculator, let's see here, 1,120 divided by 8 gives me a total of 140. That would tell me that x equals 140. And what is this? This is inches cubed. This is the volume of the smaller prism here. 140 inches cubed. Okay? All I'm doing when I'm doing this is I'm taking the ratio of the sides and taking it to the third power. Why the third power? Because it's volume. Everything in volume deals with something to the third power. Okay? Here, I've got two cones. It says find the volume of cone V, the bigger one, if cone U is 256 pi is the volume here. And we're trying to find the volume of V. Once again, I'm going to write down the side ratio. 12 over 15. Now, that's not one of the sides, that's the height. It doesn't matter. It's the same on both of them. It's used in the calculations. If you change that in ratio to each other, that's what you're going to get. 12 over 15, well, that simplifies a little bit into 4 over 5. I like dealing with 4 over 5 better. And since we're talking about volume here, I'm going to take 4 over 5, and I'm going to take it to the third power. And that 4 over 5 to the third power, well, that's 4 to the third power divided by 5 to the third power, is going to be equal to the 256 pi over some x. And this x will turn out being the volume of the bigger cone. Now, how did I know to put 256 over x? Notice how I've got 4 over 5. I've got the smaller one and the bigger one. Smaller one, bigger one. I'm trying to find the bigger one. The x went on the big one. That's where I was going. Okay? So Now we got a little bit of work we can do here. We can do cross multiplication, but we also need to figure out what these are. So 5 cubed is 125, and 4 cubed is 64. So what do I got here? I've got 64, oh, come on, right place, 64 over 125 equals 256 pi over x. Sorry about that, some virus stuff popped up on my computer there. Okay, so now doing cross multiplication here, I get 64x is equal to 125 times 256 pi. I'm going to divide by 64, so x is going to be equal to 125 times 256 divided by 64 times pi. Well, that seems fairly reasonable. So what I'm going to do is I'm going to use my calculator, and I'm just going to multiply all that out. 125 times 256 divided by 64 is 500. So what am I going to wind up with? I'm going to wind up here with 500 pi. And that would be x. That would be the volume of the larger cube here. 500 pi centimeters cubed would be the volume. Cool? Now I want you to notice something. I did not stick 3.14 in for pi. I did not at any time worry about that. I just left it as a variable, carried it all the way through my calculations, and wound up with an answer with pi in it. That is the way you treat this. You always carry that pi through. Okay? Now I want to make certain you're aware of just a couple of things. If I were looking at surface area here, if I were wanting to know the surface area, I would have taken that same 4 over 5, but I would have squared it. Why is there a difference between squaring and cubing? Well, this deals with volume. This one deals with area, so surface area. And that's the way you would be able to do the surface area, the same way as you're doing the volume here. Okay? Well, that would be the last lesson in Unit 3. Okay? So I want to make certain I do a quick review of Unit 3 so that we can make certain we all understand everything that's going on. So this is one of the questions that you might see that deals with the side-splitting theorem. It says that PL, well, where's PL? PL is this line right here in blue. PL is parallel to AE, that'd be this line right here, and to RT. They're all parallel to each other. One way you might see that if you were looking at this and they didn't want to give you this information, they would draw arrows like this on it. Okay? And that would show you that all three of them are parallel to each other. So they want you to set up some ratios. They're telling you that PA is equal to 8. They're telling you that PR is equal to 24. And they're telling you that LT, the whole distance over here, is equal to 6. Well, one of the things you could set up would be to say, well, that 8 is to 24. Wait a second, we don't have that. Is to 32 as LE is to 6. Why did I get 32? I added the 24 and the 8 and got 32 there. Why did I need that? Well, the 6 represented the whole length LT. I needed something that represented the whole length here PR, 32. So I added those two values together. What if I didn't want to do that? I could have said 8 is to 24 as LE is to 6 minus LE. How did I get that? Well, I subtracted the LE from the 6 to find what ET was here. That's 6 minus LE. And that way I could relate it to the 24. So there's several different ways you could go about solving these type of problems, but the idea is you're either going to find LE or you're going to find ET. That's what the concept is. Okay, let's look at an application problem. It says the phone company worker needs to know the height of a cell tower, so he decides to use a 4-meter pole. He took a 4-meter pole and just drove it in the ground. Well, it's probably longer than 4 meters, but when he drove it in the ground, it was 4 meters above the ground. Very smart line worker right there. So it's 4 meters up there. He knows that the distance from here to this point where it ends out here is 5 meters. He's looking at the shadow, isn't he? Because this would be the sun sitting up here, right? Sun shining down, shadow coming down here. He can use some ratios. So let's look at, we're wanting to know the cell tower, so I'm going to call this one x. We go x divided by 4 would be equal to, let's see here, we want the entire distance all the way out to here. That's going to be 45 divided by 5. I think we could probably do this by using the cross multiplication, means and extremes. We're going to get that 5x is equal to 4 times 45. And so that's 5x is equal to 180. And that x is equal to 180 divided by 5. Let's see, that's going to be 36 is equal to x. That means the cell tower is 36 meters high. Do you see how I use the ratios to find that? A little bit of an application, makes a little bit of sense. Okay, let's set up some ratios with this one. So we know that this is equal to this. Note, I'm always looking at these things that are equal. And that this is equal to this. They're giving me that AF is 16. They're giving me that FE is 4. They're giving me that AG is 12. I'm sure that they're wanting to know what this one is right here, GD. So one of the ratios you can set up is that 16 is to 12 as 4 is to x. Okay? How did I get that? Well, I took this number to this one and this one to that one. We could rearrange this in a couple of different ways, but essentially these are the types of ratios you can write with these, especially when you know you've got equal parts here. Okay? Okay. What is the scale factor large to small? What is a scale factor? A scale factor is when we take a ratio that tells us how we're going to make something get bigger or smaller. Okay? So what we're looking at here from large to small, I can see that I've got 20 centimeters here and 12 centimeters here. So I'm going to say 20 over 12. And that's going to be equal to 5 over 3. That's what I would say is the scale factor, is 5 over 3. Okay? And then it says, what's the ratio of the area? Remember, for area, we square things. So we take 5 over 3, and we square it, and that's going to give us 25 over 9. That would be my area ratio. Okay? They're that easy to do. Let's go on here. Let's look at a dilation here. If dilation transforms the pre-image ABE, so I want to make certain we know which one's the pre-image. So let's see here, from A to B to E. The yellow one here is our pre-image. To create an image ADC, well, that means the bigger one is the image ADC. Okay? And so what are we looking at? It says identify pre-image points, identify image points, and what type of a dilation is this? Well, it is an enlargement, right? So let's see here. Pre-image points are A, E, and B. The image points are A, C, and D. And what type is this? It's an enlargement. Cool? Cool. So let's look at this one. If we're looking at just a line like this, can we actually use dilations on a line? Sure. And I want you to notice it's just going down like that, and it's going like that. So we are getting, we're going to be changing the size here, right? So the pre-image with endpoints at 1, -3. So this one is my pre-image right here. There, yellow. This one is my pre-image. Okay? And we're going to dilate it. Does dilation mean it gets smaller? No, not always. Sometimes they get bigger, right? So that is my image. Image meaning the after. The pre-image would be what comes before. So it is dilated with endpoints 2, -6, and 4, 4. What is the scale factor? Well, one of the things you can do is the scale factor works with the points as well. So I can say if I go from 2, 2 to 4, 4, what did I have to multiply this by? Well, I had to multiply it by 2, didn't I? To be able to get that 4, 4. Let's try it on the other one. So we go from 1 times 2 gives me a 2. -3 times 2 gives me a -6. And that would work. Okay? So my scale factor is 2. Scale factor is equal to 2 because it doubled everything. Cool? You seeing how that works? Volume and area. The volumes of two similar solids are 20 centimeters cubed and 540 centimeters. What is the ratio of the corresponding sides of the figure to the smaller figure? So we're looking at the larger figure to the smaller figure. So I'm going to write 540 over 20. And let's do a little bit of reducing here. So that's going to be 27 over 1. Okay? Now, is that the scale factor? No, because remember we're looking at volumes here, right? Because we got the volumes of two figures. So I know that my scale factor cubed is going to be equal to this. So what times what times what gives me 27? Well, that would be 3. What times what times what gives me what? 1. So 3 over 1 cubed would equal 27 over 1. So my scale factor in this situation is 3 over 1. And that's how I find that scale factor, 3 over 1. And that's what I'm saying down here at the bottom. Okay? Cool. Now, on the coordinate plane, the origin is the center of a contraction. What does that mean? Golly, that's a little bit confusing, isn't it? No, it's really simple. So I've got a coordinate plane right there. We're going to use this point right here as my center of my contraction. Okay? So if I'm looking at a point sitting out here that is at x, y, and I'm going to go through that center here, it means it's going to go back out here somewhere. Okay? Now, we've got a scale factor of p. Okay? So essentially what we're going to be doing is we're going to be going this way with it. So all you've got to do is take px and py, and that would tell you where the new point is located. Now, a couple of things here. If p is a positive number, then my scale factor is going to cause it to go out this direction. If p is a negative number, it would cause it to go this direction. Cool? We don't really know. We're just using this as a generic term. Okay, similar triangles. It says define. I've got angles equal in two triangles. That means all the angles in two triangles are going to be equal. All the angles in two separate triangles are going to be equal to each other. And the sides between the two triangles are all proportional to each other. That's the definition of similar triangles. Okay? That means if I've got two triangles sitting here like this, that means that all of the angles, this angle up here, will be the same as this one here. This one down here will be the same as this one here. And this one here will be the same as this one here. All the angles are going to be equal to each other. Okay? And my ratio of the sides, this side will be in ratio to this one. This side here will be in ratio to this one. And this side here will be in ratio to this one. Now, to prove two triangles are similar to each other, do we have to go through and do all of these? That's three things there and three things there. I got to prove six things as being true. And the answer is no, not necessarily. You don't necessarily have to prove six things being true. Remember, we had a couple of acronyms that we could use in this situation. One of them was angle similarity. So if I just prove two angles are congruent between the two triangles, then all three of them are congruent, right? And then we can say the triangles are similar in nature. Or we said if we could prove angle side angle, or side angle side. Those are the things we would need to do to prove these triangles as being similar to each other. Okay? Let me give you another example here. This is a building, and they're wanting to know how high is the flagpole here, because we know how high the building is. So what we're going to do is we're going to draw a line from C up to through the flagpole right up to there. See how it touches the top of the flagpole? And what they're looking for is when the sun is casting this shadow, it hits right here at C, and the building's shadow and the flagpole shadow are at the same point. So let's set up a couple of ratios. One of the ratios we could come up with is 76 divided by 57. Where'd the 57 come from? Well, I needed this whole triangle distance from here to here. And so I added 48 and 9 and got 57. And that's going to be equal to the height of the flagpole divided by 9. Now it's just a matter of working this out. And you just do cross multiplication. 9 times 76 divided by 57 is going to be equal to x. Okay? And so I can work this out in my calculator. 9 times 76 divided by 57 is equal to 12. So that flagpole is 12 meters high. Cool? Okay, well, we're making progress here. So let's look at the ratios of volumes again. Okay, in this particular one, they want to know the ratio of the sides. I'm looking at this and I see 45 and I see 36, so my ratio is going to be 45 over 36. Now wait a second, those are both divisible by 9, aren't they? So what are we going to get? We're going to get 5 over 4. There's my side, there's my scale factor. That's the ratio of the sides, 5 over 4. Now if I want to get the ratio of the area, no problem. That's going to be 25 over 16. All I did was take 5 over 4 and square it, and that would be the ratio of the area. Now if I want to find the ratio of the volumes, no problem. 5 over 4, and we cube it. That'll be equal to 125 over 64. Do you see how easy these two are once you have this one? Hope you see how that if you did it the other way around, if you knew this one, you could find these two. It's not that difficult a process to go backwards on this situation. Okay? A few more problems in my review here. It says, what theorem and what values? Well, if we're asking me to prove the triangle similar and they want to know what theorem I'm going to use, I noticed that they gave me that this angle is the same in both of these two. Okay? And then I noticed that 4.5 divided by 1.5 is equal to 3. And that 5.4 divided by 1.8 is equal to 3. So this side is in the same ratio as these two sides. And now just looking at what I've got written on both triangles, my theorem is going to be side angle side similarity. It's not that hard to come up with that. Cool? And I know my printing is difficult to read there on this particular problem. That is a 54. 5.4. Excuse me. Cool? Okay. So what would the part 2 problems look like? Well, you're going to have a side splitting problem. What does that mean? Any one of these problems that I've worked in here today where I've taken it and I've found the ratio and found a different side, that's a side splitting problem. You're going to have one that deals with the scale factor, the area and the volume scale factor. That means I'm going to give you enough information to find the scale factor for two sides, and you've got to find the scale factor for the area and the scale factor for the volume by squaring it and then by cubing it. Remember that? You can go back and look at the examples that I've done in this review, and it'll help you a lot. Okay? Okay, and if you're in 203 or 204, you're going to have one more, and that's going to be finding the side lengths using the side splitting formula. So it's going to be just using that side splitting formula one more time to find some missing values. Cool? Okay, well, let's move on to chapter 4 just a little bit here. I don't have a lot here, just a couple of slides, but I want to make certain I introduce chapter 4 because you're going to be doing that Wednesday, Thursday, and Friday. They want me to name each part of the circle. So let's see here. If I were looking at AD, and see how it's got a straight line above it? AD is the diagonal. Okay? Or the diameter. It's not a diagonal, it's a diameter. Jeez. Mr. Green, what are you thinking? I'm thinking I'm sleepy. It's a diameter. It goes all the way across the circle, right? If I'm talking about PB, from P to B there, that is a radius. It goes halfway across the circle, right? Starts at the center and goes out to the edge. If I'm looking at BD, that is called a chord. A chord is a length that goes across the circle, but not through the center. Well, in actuality, AD is a chord as well, but it's a special chord called the diameter. BD is just a chord. Now I want you to notice, PB is not a chord because it doesn't go all the way across the circle, does it? Okay, they're asking about BPD. From B to P to D, that's this angle right here that they're asking. What is that called? Well, see how it's got an angle it starts at the center of the circle? This is called a central angle. Okay? Now they're asking about BDA. BDA. This one is out here on the outside of the circle. See how it's touching the outside edge of the circle? That would be considered a inscribed angle. Okay? You need to make certain you understand what a central angle and an inscribed angle are. A central angle will always have its vertex sitting at the center of the circle. The inscribed angle will always have its vertex sitting on the edge of the circle. Okay? And point P is the center of the circle. Okay, vocabulary terms. Make certain you know what these are here. Make certain you know what these are here. Those are all vocabulary terms that we're going to be using in Chapter 4 a lot, so you need to make certain you know them. Okay? So, that is a messy diagram. Well, they're telling me EF is the diameter. It goes all the way across of the circle, and that of circle D. When they say something like this, of circle D, that means D is the center of the circle. So we actually know where the center is located right there. Okay? And they're telling me that angle GDE, okay, see how I touched each one of those as I went by them? GDE, that's this angle right here, is 105 degrees. And they're wanting to know the measure of this angle right over here. No, they're wanting to know the measure of this arc right up here, right? Well, one of the things that you'll find out when you go through the lessons is if I've got a central angle, central meaning it's at the center, which this is, the measure of the central angle is also the measure of the arc. They're the same. So since I know that EF is a diameter, that's a straight line, that's 180 degrees. I can take 180 minus 105, and I get 75 degrees. This angle in here is 75 degrees. That means this arc out here is 75 degrees. That's how arcs are measured in degrees. Okay? Arcs are measured in degrees. But arc lengths are a length, and we will talk about how to find that length also. Okay? So let's look at this one. It says circle D has a diameter of EF. So there's the center, and there's a diameter going across there, right? If GDF, let's see here, GDF, that's this angle right here, is 55 degrees. What is the measure of arc EH? EH. That's this one here. Well, theorem that you're going to get in the course. See how this chord equals this chord right here? That means these arcs are the same length as well. So this one's 55 degrees, and this one out here would be 55 degrees as well. Okay? Now they're saying C, D, E is 120 degrees, and they're wanting to know the measurement of E, G, C. Well, what's going on here is that this arc out here, I'm going to change colors pen so you can see it. Okay, so this arc here from E to C, that arc is 120 degrees. And they're asking me about this arc here in blue, EGC. Well, that's the rest of the circle, isn't it? So I could actually take 360, because that's the whole circle, minus the 120 and get 240 degrees, and that would be the measure of that arc. Okay? I want you to notice what they're doing down here. See how they're making arcs with these little curved lines above them? I also want you to note if it's a two-letter arc, it means it's relatively short. If it's a three-letter arc, that means it goes a long way around. You have to go through the letter that they're telling you to go through. Okay? Okay, so I now have a lot of things in there that are kind of confusing. Okay? I want to select those and get rid of some of these so that we can see what's going on in here. There we go. Now, next question, it says, if the measure of EH, so that's this arc right here, is 43 degrees, what is the measure of angle GDF? This angle right here. Well, this is the same thing as what we did up there in number 1. Because these chords are the same length, that means this arc here is going to be the same, 43 degrees. And since this is a central angle, it's going to be the same as the arc, 43 degrees. Okay? So I've thrown several theorems here at you in these last 3 slides. Some vocabulary and a couple of theorems that you're going to need to understand. As you're reading through Unit 4, make certain you read it and make certain you watch the video that I have out there on it. You will get to understand these theorems. We will be using these a lot. As you can see, the diagrams a lot of times on these can be quite confusing, and you've got to be real careful with them, making certain that when it's giving you something, you touch all 3 points of it or 2 points of it, and you know what they're talking about. It's one of those things where you're going to have some confusing diagrams to help you try to understand what's going on. Okay? So I'm sorry I couldn't be with you this week. I will be with you again next week, and we will go over some more of this stuff and continue on with Unit 4. I'll talk to you then. Bye.